Now, we remember de Broglie's hypothesis. The electron has a wavelength, lambda, that is given by Planck's constant divided by the momentum. And we wrote down the value of Planck's constant here. This is as many decimal places as it's known to with any accuracy. Often for calculations, we'll just use 6.626 times 10 to minus 34. Now, what we want to do is use de Broglie's hypothesis to help us construct a wave equation. So let's do that. And what we're going to do is we're going to construct a Helmholtz wave equation here. So we're going to consider waves of only one wavelength for the moment, a wavelength lambda. That is monochromatic waves. And with our Helmholtz wave equation, here's a Helmholtz wave equation that we might choose to write down, where we've got k equals 2 pi over lambda. And we know this works for simple waves. We're hoping it's going to work for our quantum mechanical waves here. And it's got solutions like sine kz, cos kz, e to the I kz, or the same things with minus signs. All of those are solutions of this equation, at least until we put some boundary conditions in. So in 3 dimensions, we know we generalize this as del squared psi equals minus k squared psi. So again, we're postulating that we think we can construct a Helmholtz wave equation here that may work for us. And again, this one has solutions similarly, sine k dot r, cos k dot r, e to the I k dot r. And we checked that out before. And also with the minus signs in front, these are all solutions. And of course, k and r here are vectors. But this is a simple 3-dimensional version of a Helmholtz equation. So we take our de Broglie's hypothesis, our definition that k is equal to 2 pi over lambda. We're going to use k's instead of lambdas mostly. Then k is equal to 2 pi times the momentum over h, or k is equal to p over h bar. In fact, often you will get used to thinking of h bar k as being the momentum, so that would be taking h bar over to here. Anyway, this is our definition of k here. And h bar, as we've said before, is h over 2 pi. It's a convenient unit to use often. So with all of this, k squared is equal to p squared over h bar squared. Hence, using de Broglie's hypothesis and choosing to write things in terms of k's instead of lambdas, we have our proposed Helmholtz equation is del squared psi equals minus p squared over h bar squared psi. Or equivalently, we can take the h bar squared and the minus sign over to this side, get minus h bar squared del squared psi equals p squared psi. We're just postulating this, remember. If we were thinking explicitly of an electron, we can divide both sides of this equation by the mass m0 of the electron. Nobody can stop us from doing that. It's mathematically perfectly legal. So then we have minus h bar squared over 2m0 del squared psi equals p squared over 2m0 psi. Now, we know from classical mechanics that this p squared over 2m0 is classically just the kinetic energy, in this case of an electron, of a particle with mass m0. And in general, we know from classical mechanics, and we hope it's going to work here in quantum mechanics as well, that total energy, which we could call E, is just the kinetic energy plus the potential energy, and we'll call the potential energy V of R. So, kinetic energy is total energy minus potential energy, obviously. Hence, our Helmholtz equation that we had been working on before would become what we're now going to call the Schroedinger equation, substituting in for p squared over 2m0 with E minus V of R. We get this equation here, that's a substitution on the right, or equivalently, this equation here. It's the same equation. This is perhaps a more common form of writing it, but both of these are used. This is a Schroedinger equation. We've just postulated this, remember. We've said, let's take de Broglie's hypothesis And let's see what happens if we try to construct a Helmholtz wave equation using that for a monochromatic wave. And this is our result. And this is, in fact, Schrodinger's equation. This is technically what's called the time-independent equation. And we can go on if we want. We did this presuming we were working with an electron just for definiteness, but we can postulate that we could have a Schrödinger equation for any particle of mass m. So we'd have, instead of m naught here, we'd have just the mass of the particle. And this would be our time-independent Schrödinger equation for that particle. As I said, formally, this is the time-independent Schrödinger equation. We'll look at the time-dependent Schrödinger equation later on.
Note that we've not derived Schrödinger's equation. We've merely suggested it as an equation, one that agrees with at least one experiment. It's important to understand there's no way to derive Schrödinger's equation from first principles. There are no first principles in the physics that precedes quantum mechanics that predicts anything like such wave behavior for the electron. Schrödinger's equation just has to be postulated, just like Newton originally postulated his laws of motion. And the only justification for making such a postulate is that it works. Now that we have a wave equation, it might seem we're almost back into a classical world. After all, sound waves, water waves, electromagnetic waves, and possibly many other kinds of waves have straightforward classical meanings. Meanings in terms of amplitudes of some quite real physical quantities that we can measure. For sound waves, it would be air pressure. For water waves, it would be the height of the surface of the water. For electromagnetic waves, it might be the electric field strength, and so on. The interpretation of our quantum mechanical wave is, however, not apparently so direct. Indeed, it's not even clear if we can measure this wave itself, and consequently, it's really not directly clear what its meaning might be. This was a puzzle for the early workers in quantum mechanics, and to be honest, it remains somewhat of a puzzle to this day. In 1926, Max Born came up with an idea that has, however, turned out to work very well empirically. Indeed, this is our main tool in deducing measurable quantities from quantum mechanical calculations. He postulated that the modulus squared of the wave function at some point was proportional to the probability of finding the particle, an electron for example, near that point. Now, this is a purely probabilistic interpretation of quantum mechanics. That bothered people then, and it still bothers them today. In particular, Einstein did not like it, and he made a statement in objection to it that is much quoted in a paraphrased form as, "God does not play dice." What he means by that is perhaps even that if we only currently have a probabilistic interpretation, maybe underneath it there is some real deterministic definite theory. And we're only seeing sort of a statistical reflection of that underlying theory. Now, there's a precedent for that in ordinary classical physics. We see pressures and temperatures, and those are reflections of the underlying, in the classical view, presumably definite positions and momentums of atoms and molecules. That's merely a statistical view that we are seeing. So the temperature in a gas is merely a statistical reflection of an underlying theory that is in fact much more determinate based on actual positions and momenta of gas atoms or molecules. Now, whether Einstein's wish for this more determinate underlying theory will come true is still an open question, and in fact the current predominant view is more towards the probabilistic interpretation maybe being as good as we can get. Whatever the philosophical questions here, the good news is that as far as we are aware, this probabilistic interpretation does indeed give us an empirical interpretation that works. And indeed, it works very well. So let's look at Born's proposal.
Specifically then, Born's postulate is that the probability, P of r, of finding an electron near any specific point r in space is proportional to the modulus squared of the wave amplitude. This modulus squared of the wave amplitude can therefore be viewed as a probability density. Now, that in itself is a reasonable concept in ordinary probability theory, and we're just choosing to propose that we interpret the wave function that way here. But this idea of something being the modulus squared of a complex quantity to represent probability density, this quantity of which we're taking the squared modulus does not really have an analog in conventional probability theory, but we're going to call it probability amplitude here. Or more generally, we'll talk about things like the wave function here as a quantum mechanical amplitude. And in general, we'll be taking the modulus squareds of these to get to real measurable physical quantities, such as a probability density. In principle, we can measure this probability density by doing a bunch of experiments.
Using the squared modulus assures that we always have a positive quantity. And that's a good thing because we would not know how to interpret a negative probability. It's also consistent with some other uses of squared amplitudes with waves. For example, the squared amplitude often tells us the intensity or the power per unit area or energy density in a wave motion, such as a sound wave or an electromagnetic wave. We would also find in electromagnetism that the probability of finding a photon at some specific point was indeed proportional to the squared wave amplitude. And if, when we are describing classical waves, we choose for convenience to use a complex notation, we use the modulus squared of that classical wave amplitude to describe the wave intensity, and hence also the probability of finding the photon at a specific point in space. However, this analogy is a little dangerous because our quantum mechanical wave amplitude itself, unlike an electromagnetic wave amplitude, does not apparently correspond to anything measurable. For now, we think of that probability amplitude as being the amplitude of a wave. We will later on find that this concept of probability amplitudes that we are taking the modulus squared of extends into quite different descriptions, but still retaining the concept, the modulus squared representing a probability as Born had proposed for us.